Now that we've covered what limits are, we can move forward to develop an understanding of what derivatives are from first principles. Specifically, we'll start off with the delta method. The delta method is a technique that allows us to use limits to identify the slope of a line at any given point along a curve. We will use this curve here, which we've actually already seen before, and identify the slope right here at this point using the delta method in a hands-on code demo now. And we'll use that then to move onwards to derive this formula here, which is the most common representation of the formula for derivatives. For this example, let's bring back our old buddy y equals x squared plus 2x plus 2. So I'm going to define this as the function f now. And you can just see x squared plus 2x plus 2. That's all that we've got here in this Python function. So now we can pass our x values, which we've already used a number of times in this notebook, through that function to create our y values, and we can plot them out. So here's a curve that we've already seen a few times. We've used it to find the slope here around -1 before just by zooming in at the top of this notebook. But now let's use this curve more generally to identify the slope at any point along the curve, let's say where x equals 2. First, we can use our function f to determine what y is. So, okay, at this point, x equals 2, y is equal to 10. And we can call that point there 2, 10. So x is equal to 2, y is equal to 10. And we can plot that point out. So here it is, exactly there. The delta method uses the difference between 2 points to calculate a slope at a given point. So we're going to calculate the slope here at this point, at the blue point where x is equal to 2 and y is equal to 10. And the delta method involves now using a point somewhere else. So you can define this point anywhere else on the curve. The closer you get to the target point, the more accurate the approximation of slope is going to be. But to illustrate that, let's start somewhere where the other point is a little bit further away. So we're going to call this point Q, and let's say it's at x is equal to 5. So it's going to end up being right here. So again, we can calculate what y is equal to very precisely using our f function. So it's going to be equal to 37, where x equals 5. And now we can plot both our point P at 2 and 10 and our point Q at 5 and 37. I'm using orange for the Q point, the second point. So let's find the slope m between the points P and Q. So the equation for slope is change in y divided by change in x. We've seen this from the very beginning of these live lessons with the example of the vehicle driving away from home. So in that case, it was distance over time. Here it's change in y divided by change in x. We can use the symbol delta to denote change in y. So delta y is the same as change in y, delta x is the same as change in x. And specifically, we can have this be the difference between our 2 points, y2 minus y1 for the change in y, and x2 minus x1 for the change in x. So using the points here, we have 37 for our y2 and 5 for our x2, representing point Q. And then for point P, we have 10 for our y and 2 for our x value. So I just plug those values in here into our formula. y2 minus y1, 37 minus 10 comes out to 27, and x2 minus x1, which is 5 minus 2, comes out to 3. 27 divided by 3 is 9. So this means that the slope of the line between these 2 points, P and Q, has a slope of 9. M is equal to 9. So we can do the same math here that we did with kind of by hand. Here we can do that with code as well. And then we can plot the line that passes through P and Q. Now that we have the slope M, we can rearrange the equation of a line, y equals mx plus b, to solve for the only term that we don't have yet, b. So we have y, we can use the y or the x from either p or q. So we have y and x values available to us. We now have m. All we need is b, so rearranging y equals mx plus b to isolate b by moving mx to the other side of the equation, we now have b equals y minus mx. So to calculate b now, we have m already. We know that's 9. You can grab the x and y from either point, p or q. So, let's grab them for q, 37 and 5 for our y and x values respectively. Y and x values respectively gives us b. So b, the y-intercept for this line, is going to be equal to -8. Now, using all of these variables that we have, specifically m and b, the two parameters of the line, we can now plug our x vector, which is 1,000 points ranging from -10 to +10, in the y equals mx plus b equation. So m times x plus b is going to give us a line of y's. And we can plot that in here. So now we have, using our vector x and vector y, we can plot the line y in orange alongside our curve here. So clearly, the line, we've succeeded. All of the arithmetic that we've done was correct, and we've found the slope of the line that passes between both of our points, p and q. So as I mentioned earlier, the closer q becomes to p, the closer the slope m comes to being the true tangent of the point p. Let's demonstrate this with another point q that's much closer to p. So p is at x equals 2, so instead of having q be at x equals 5, let's bring q much closer now to x equals 2.1. So previously our delta x between q and p was equal to 3. Now it is much smaller. It is just 0.1. Just as we passed that x value of 5 into our function, we can pass in the 2.1. That comes out to give us a y value of 10.61. So now when we plot our 2 points p and q, we see that they're very, very close to each other. So p is still at 2 and 10, and q is now at 2.1 and 10.61, right here. We can calculate our slope using the same formula as we did earlier. Now our slope comes out to 6.1. And using one of the formulas we used earlier for p and q, we can now calculate the y-intercept b for the line that passes through the points p and q, and we can plot that, just as we did previously when p and q were further apart. So now that p and q are much closer, as the delta x has begun to approach 0, so as the distance between these 2 points along the x-axis approaches 0, it becomes clearer that the slope m at point P is equal to 6. So our slope is coming out as 6.1, but the smaller we make the delta, the more clearly we can see that the slope is 6. So let's now make the delta x, the difference between P and Q along the x-axis, extremely small. So 0.00001 to illustrate that this statement I made is true. So let's set delta x equal to that number that's very close to 0. And now we can take our point P, we can split it up into its x1 and y1 elements. And we can rearrange our formula from above that delta x is equal to x2 minus x1. We can rearrange that to calculate the x2 for our point Q, which is now going to be extremely close to P. So to isolate for x2, we just move x1 over to the other side of the equation, giving us x2 is equal to x1 plus delta x. So here's that same formula in code. x2 is just going to be the x1 plus delta x, which gives us a value just a tiny little bit larger than 2. And then for our point Q, we can obtain y2 in the usual way using our function f. To find the slope m, we can continue to use the formula from earlier for slope from 2 points. And as we can clearly see, the slope has become very, very close to 6 now. There's no question that as the delta between our 2 points decreases, we can see that our slope converges upon a slope of 6. Now, as a comprehension exercise, given everything that we've covered about the delta method so far, you should be able to find the slope of the tangent of this same function that we've been looking at so far, x squared plus 2x plus 2, to find the slope of the tangent where x equals -1 on that curve instead of where it is equal to 2. Now's a good time to stop the video and take a crack at it, because the answer is just a few cells below in this Jupyter notebook, and I'm about to go over it.